Hello class. In this short video, we will discuss about diode clippers. Diode clippers, also called as diode limiters, are going to clip portion of the signal above or below depending upon the specific type of application, which are necessary where you will see a supply voltage is larger than needed in order to prevent the overloads. Let's say I have a circuit that requires 6 volts peak to peak, but my input signal is like 10 volts peak to peak. So I can clip the portion of the input signal. So I can clip the 10 volts peak to peak into a 6 volts peak to peak signal. So I can clip either positive side of the signal or the negative side, or also the both ends of the signal depending upon the application. A diode limiter can be used along with a DC power supply, which can control the amplitude of the signal if it is too large by either clipping one half of the wave or both half of the wave. So the advantage of the diode clipper is the precise reduction in the amplitude. So there are various types of these clippings are possible. For example, if I consider an input signal, a normal sine wave, if I look at the positive clipping, I can clip the positive side of the signal. Again, you can clip any voltage you want. So in this case, let's say for example, I can clip the positive wave, but I can allow the negative cycle. And in the negative clipping, I can keep the positive half cycle, but I can clip the negative half cycle. And in this case, you can clip both sides of the signal. The amplitude of this clipping can be adjusted. So for example, if you want to clip it right there, you could do that. So the amplitude of this clipping, again, I can increase the clipping, or I can clip like this. So the voltage levels that I'm clipping could be easily adjusted. So let's look at how this positive clipping works. So this is a circuit where I have a power source, an AC power source with 5 volts peak, a 10 kilo ohm input resistance, and a diode, and a 10 kilo ohm load resistance. If you observe that this diode and the load resistor are parallel to each other. So the diode is parallel to the load resistor. So that means whatever the voltage across the diode is, the same voltage will appear across the load resistor. If you remember that voltage across the parallel components are going to be equal. So if I consider the positive half cycle of the signal, so I have two loops in here. The first loop consists of the source, a resistor, and a diode. And the second loop is just a diode parallel to the resistor. So during the positive half cycle, if you look at the first loop, so that means that's the positive half cycle being applied. The diode will be forward biased. So because the voltage at the anode, so that's the orientation of the diode. So this side is going to be the anode and this side is going to be the cathode. So the positive half cycle, the diode will be forward biased. So remember that when the diode is forward biased, a forward biased diode, so if I assume it's a silicon, if it is a forward biased, its forward voltage is going to be 0.7 volts approximately. Because the diode is in parallel to the resistor, the voltage across the resistor is going to be just 0.7 volts during the positive half cycle. So that's why you will see here when the input signal is positive half cycle, the output is just 0.7 volts. So it's clipping the positive half cycle. During the negative half cycle of the signal, so meaning that I am applying a negative potential right here, but still that's an anode of the diode, this is a cathode. So in the first loop, during the negative half cycle, the diode will be reverse bias. Again, remember that when the diode is in the reverse bias condition, it will act as an open circuit. If I redraw this circuit, so because I'm talking about a negative half cycle, the diode will be reverse biased. So I have a 10 kilo ohm resistor here, and I have another 10 kilo ohm resistor and a 5 volts peak signal. So again, if you observe the input current, again I'm talking about a negative half cycle. So the input current coming from the source flows through this resistor, but when it enters this node, it cannot go towards the path of the diode because the circuit is open. So meaning that the whole current will flow through the actual load resistor. So meaning that this circuit is similar to, so I can basically completely erase this part of an open circuit. So the circuit is very similar to like this. So I have a a 10 kilo ohm resistor right there and another 10 kilo ohm resistor. So if you observe that these two resistors are in series, because I'm finally looking at voltage across this load resistor, because that's where the load is. So if you look at this circuit, it is a series circuit. Two equal values of the resistors, both are 10 kilo ohms, will split the input voltage exactly into half. So meaning that the output voltage will be 2.5 volts during the negative half cycle. So if you observe, if the input signal is negative, the output voltage is not same as an input, but it's exactly half. The reason is here I have a two 10 kilo ohm resistors in series to each other. They become series because the diode becomes open during the negative half cycle. So that means in this case I have a zero point 0.7 volts during the positive half cycle and 2.5 volts during the negative half cycle. So this circuit is referred as positive clipping. Let me consider a different example. Let's say I have a 10 volt peak signal connected through an input resistor and I have a diode positioned like that, and I have a load resistor which is parallel to the diode. So let's say for example I have a 1 kilo ohm input resistance and 2 kilo ohms load resistance. So let's say for example we are trying to find out the output voltage across this load resistor. You always need to split the problem into two halves. One is with respect to the positive half cycle and the another one is with respect to the negative half cycle. So I'm going to split into half. So this one I'm going to talk about the positive cycle of the input, because remember that input signal is an AC signal, and I'm going to talk about the negative half cycle. So during the positive half cycle, so meaning that positive signal is applied to the diode. Again, the orientation of the diode is important. So here I have an anode and a cathode. So during the positive half cycle, the diode will be forward biased because you are applying the positive voltage to the anode and a negative to the cathode. That will make diode forward biased. So meaning that because this leg has only one single diode which is parallel to the load resistance. So whatever the voltage across the diode is, the same voltage will be appear across the load. So during the positive half cycle, diode will be forward bias, so which consists of a forward voltage drop of 0.7 volts. So meaning that during the positive half cycle, all I'm going to see is 0.7 volts. So during the negative half cycle, meaning that the input signal I am applying is going to be a negative. The orientation of the diode will be the same. So that means the diode will be reverse biased. So if the diode will be reverse biased, then I'm going to redraw this circuit in order to understand what is the value. So reverse bias means the diode will be open. Always remember that when the diode is reverse biased, it will always act as an open circuit. So now I have a 2 kilo ohm here and I have a 1 kilo ohm resistor and I have a 10 volts peak signal. So if you observe, because it's an open circuit, there is no current flows through this branch of the circuit. So that means I can simply erase that portion of the circuit. So that yields us a simple series circuit. All we need to do is find the voltage across the load resistor. So in this case, the load resistor is the 2 kilo ohm resistor. So it is a simple series circuit. In the previous example, we split this voltage into half because there the resistors values are equal, but in this case the resistor values are different. So what we can do is we can apply voltage divider. So the voltage across the load resistor is equals to total source voltage times the load resistor divided by, if you observe these two resistors are in series, total resistance is sum of the two resistors. So in this case 1K plus 2K, it's a total of 3 kilo ohms. So you will see 6.66 volts. So during the negative half cycle, all I'm going to see is there is not going to be any clipping, but what I'm going to see is 6.66 volts. So again, this particular circuit is a positive clipper because the positive peak is going to be adjusted. So it will only clip the positive half cycle, but it will not clip the negative half cycle. So that is the positive clipping. As the input signal goes positive, the diode becomes forward biased and conducts the current. So because that's the anode and the cathode of the diode, and a diode acts as a zero point 0.7 volt source, so the voltage across the resistor will be 0.7 because it is parallel. Remember that across the parallel, the voltage will be equal. When the input goes negative, the diode will be reverse biased and does not conduct, which will act as an open circuit. It is always a good idea to redraw the circuit by removing the diode when it's a reverse bias. So the voltage across the resistor is the source voltage minus the drop of R2. You can use the concept of voltage divider. So let me consider another example. So let's say we are looking at the output voltage across this load resistor. So during the positive half cycle and also during the negative half cycle. So you need to split the problem again into half. So during the positive half cycle and also during the negative half cycle. So during the positive half cycle, so that's the anode and cathode. So during the positive half cycle, diode will be forward biased, meaning that the voltage across the diode. So it's basically, if I even redraw in the forward bias, so the anode is on the top, that's a positive, cathode at the bottom, that's a negative. So during the forward bias, the diode is basically acting as a 0.7 volts voltage source, which is connected across that load resistor. So meaning that the voltage across the load resistor will be 0.7 volts because the diode will act as a 0.7 volt source when it is forward biased. Again, the polarity of the diode is important. If you observe the diode, the anode is on the top, so that's why that's a positive side and that is going to be the negative side of the 0.7 volts. But during the negative half cycle, the diode will be reverse biased. So meaning that if I redraw the circuit, reverse biased diode will act as an open circuit, and I have this, so a 2 kilo ohm resistance and a 5 kilo ohm resistance and a 5 volts peak signal. So the voltage across the load, again the load in this case is a 5 kilo ohms. Because the branch of the diode is open, I could eliminate that branch. That makes this circuit as a series circuit. So the voltage across the load is total source voltage, which is going to be 5 volts multiplied by the load resistor divided by these two resistors are in series. So 2K plus 5K, which is going to be a total of 7 kilo ohms. So you will get 3.57 volts. So that is the voltage across the load resistor during the negative half cycle. So 0.7 volts during the positive half cycle, 3.57 volts during the negative half cycle. So the output voltage, if you draw it, it will clip the positive cycle, but it won't clip the negative cycle. So here I have a 0.7 volts, and on the negative peak, I have a 3.57 volts. Negative clipping. As you can see, there is a difference from this circuit to this circuit where the orientation of the diode. In the positive clipping, you will see anode on the top, cathode at the bottom. In the negative clipping, you will see the cathode is going to be on the top, whereas the anode is going to be at the bottom. So meaning that it will behave exactly opposite. So instead of doing positive clipping, it will do a negative clipping. So let's observe how this circuit behave. Alright, again, let's split this problem into two half cycles, positive and negative half cycle. So during the positive half cycle, so that's what the positive and negative is. So let's point out this is the cathode and that's the anode of the diode. So you are applying the positive voltage to the cathode. So if you look at that first loop, so that means the diode will be reverse biased. So in this circuit, the diode will be reverse biased during the positive half cycle. So if I redraw it, remember that reverse bias means it will act as an open circuit. So I have a 10 kilo ohms here, I have a 10 kilo ohms there, and a 5 volts peak signal is applied. So I can eliminate, because when the diode is reverse bias, I can eliminate this whole branch. If I want to calculate the voltage across the load resistor, again this is going to be the load resistor and we are trying to find out the voltage across the load. So if you can apply the voltage divider too. So it's a total voltage is 5 volts multiplied by the load resistance, which is 10K, divided by the total resistance 20K. So you will see 2.5 volts is going to be across the positive half cycle. So when your input is positive, the output voltage you will see is only 2.5 volts. During the negative half cycle, so that means the input signal is, so if you observe that the positive is basically applied to an anode and the negative being applied to the cathode. So the diode will be forward biased. When the diode is forward biased, there is going to be 0.7 volts across the diode. So it simply means, so how, remember when it is forward biased, you need to carry the polarities. The cathode is on the top, which is the negative. The anode is at the bottom, positive. So that means when the diode is forward biased, it acts as a 0.7 volt source. So that's both resistors are 10 kilo ohms. The load is parallel to that 0.7 volt source. So the voltage across the load, if you observe that, that's the negative and the positive. So I'm going to collect a negative 0.7 volts. Look at the orientation of the diode. So that means the output voltage during the negative half cycle is going to be negative 0.7 volts. So in this case, it is going to be a negative 0.7 volts. So that is what's going to happen. So if you observe, I have a multi-SIP circuit here where this blue signal is going to be the input signal and the red one is going to be an output signal. As you can see, during the positive half cycle, I'm expecting 2.5 volts. So you can see that voltage is less than that 5 volts. And if you observe carefully, it's going to be exactly half. And during the negative half cycle, negative 0.7 volts. So that's what happening during the negative half cycle. It is going to be a negative 0.7 volts. So here the most important things are the orientation of the diode, identifying whether the diode is forward biased or whether the diode is reverse biased. So in the negative clipping, it is exactly opposite to the positive clipping. When the input goes positive, the diode becomes reverse bias and it will not conduct. And the diode acts as an open circuit. So the voltage across the resistor is source voltage minus the voltage drop across R2. Or you can use an voltage divider principle. When the input goes negative, that's where the diode can become forward bias and conducts, which is acts as a negative 0.7 volt source. If you observe, because that is because of the orientation of the diode. Here the cathode is at the top, anode is at the bottom. In the positive clipping, the anode is at the top, the cathode is at the bottom. So that's what the positive clipping is, and this is a negative clipping. So if you observe this circuit, I have two diodes are placed back to back and obviously they are parallel to each other. And it's asking what the behavior of the following circuit. So in this case, if I consider this circuit, so this is going to be the anode, that's the cathode, and here it's the cathode, this is going to be the anode. Again, I'm going to consider both half cycles, positive half cycle and also a negative half cycle. So during the positive half cycle, the D2 will be forward biased, D4 will be reverse biased. So meaning that if I redraw the circuit, so the D2 will have an anode at the top. So that means when it is forward biased, remember that it's a 0.7 volts, but anode is at the top. So that's going to be 0.7 volts. The D4 will be reverse biased, meaning that it acts as an open circuit. And finally, you have the load resistor. Again, that's a 10K. So if you remove this open branch because no current goes into it, and if you observe the load is, so again this is the load resistor is parallel to the 0.7 volts. So meaning that during the positive half cycle, the output will be just 0.7. During the negative half cycle, so that means the input signal is applied is going to be a negative. So during the negative half cycle, the D2 will be reverse biased and D4 will be forward biased. So that means if you redraw the circuit, so D2 will be reverse biased, meaning that I can replace with an open circuit. D4 will be forward biased, meaning that it consists of 0.7 volts, but the cathode is at the top and the anode is at the bottom. So that's going to be a negative and positive because it's a forward bias. It consists of that 0.7 volts across it and you still have your load. So if I remove this open circuit, So if you observe that the load resistor is in parallel, but in this case I'm going to get a negative 0.7 because observe the negative is at the top. So combined the final output voltage, or during the positive half cycle I will see zero point 0.7, during the negative half cycle I will see a negative 0.7. So this circuit will perform clipping on both ends, but the voltage is going to be 0.7 volts on each half of the cycle. So if you observe again, this blue one is going to be the input signal and the red one is an output. As you can see, the input signal clipped on both half cycles. It clipped on the positive half cycle as well as it clipped on the negative half cycle. So that's what a diode limiter saw. But if you observe on all of these circuits, the clipping voltage is always 0.7 volts because I have only a single diode placed, or in this case a multiple diodes placed across the load resistor. But I cannot change that 0.7 ohms if I want to use only one single diode, because if I use a one diode, as long as it is forward bias, I'm going to only get that 0.7 ohms. Let's say for example, if you require a 3 volts of clipping, you can eventually keep increasing the number of diodes that you are putting. So for example, if I consider, instead of putting a single diode in here in this branch, I can try to consider multiple diodes. So for example, like this in series. So that will get me, instead of 0.7 volts during the negative clipping, I will get 1.4 volts. If I put a 3 diodes, again 3 times 0.7, 2.1 volts. But it is going to give me in steps of 0.7 volts if you keep on increasing the number of diodes. But that will increases the complexity of the circuit. Let's say I don't want this 1.4, I want the clipping to be done at 1 volt. You cannot do with 1.5 diode. Right? If you use a 1 diode, you will get 0.7. If you use 2 diodes, you will get a 1.4. So how can I get that 1 volt? So that is the concept of biased limiters. So where the diode, if you observe the biased limiter circuits, a diode is connected in series with a DC power supply. So if you look at this branch, you can look at that diode is connected in series with the DC power supply, even though if you change the orientation of the diode. So this will allow us to clip the input signal other than 0.7 volts. Thanks for watching. That will conclude this lecture.